Okay, so welcome everybody to the JINA web seminar. Today's speaker is Matt Caplan of Indiana University, and he will tell us about Astromaterial Science.
Thanks for the introduction. Just before I start, I want to make sure everybody can hear me okay and that my slides are coming through. Can I get like a thumbs up from NSCL maybe? Okay, that looks like a thumbs up. Great, so I'm ready to go. All right, so thanks for having me. I really appreciate the chance to do one of these seminars. How can I get my laser pointer? That's the only other thing that I need. Spotlight, laser pointer, and you can see my laser pointer.
Yep,
Great.
yep.
Okay, so stars freeze, but not all stars. Only some parts of some stars freeze. So that's sort of the punchline. I know that some of you guys like to tweet, so if you wanted a good soundbite, there you go. This is the basic idea behind Chuck and I's recent letter that we put up on the archive, and hopefully it'll end up in RevModPhys pretty soon. But we just take principles of material science and we use them to describe neutron star crusts in a sense. So on this side, I've got what we considered a hard astromaterial. That is the ions that form the outer crust of the neutron star. And on this side, I've got a frame of nuclear pasta, which we call soft astromaterials, not because it's particularly soft, but because it has a sort of a correspondence with terrestrial soft matter systems. So again, this is up on the archive. If anybody is interested in learning more after the fact, you can just search Astromaterial Science on the archive, and almost everything I say will be in that article as well. Okay, so just to help you get oriented, to introduce neutron stars, what is inside of a neutron star? To our sort of zeroth order approximation, we take it to be this one solar mass ball that's 12 miles across or something. We say it's like a giant nucleus in space. That's what we say in our outreach talks. But there's actually a very rich substructure. You want to imagine something closer to the Earth rather than something that's like a giant ball in space. So if you start sort of at the top, you have a sparse atmosphere, thinking by this analog with the Earth. And as you descend deeper, eventually you're going to hit something that's a liquid. And if you descend through that liquid, the pressure is going to increase until eventually you hit solid. In the Earth, that would be a continental rock or the base of the oceanic plates. And in the neutron star, that's going to be a literal solid crust, which is going to be the topic of my talk. And as you descend through that solid crust, the pressure continues to increase until you hit a sort of mantle material almost. That's where we're going to find this nuclear pasta that I'm going to talk about, until you get to, of course, a liquid core. So there's sort of an analog almost with the structure of the Earth and sort of the interior structure of a neutron star. And so as you descend, you can see sort of individual nuclei here. They become compressed until they sort of freeze into a lattice. And that lattice is going to be the subject of the first half of my talk. To give you just sort of a toy model to help you get oriented, imagine a neutron star that has a crust made of, for example, iron 56. Upon compression, as you descend through the crust, so that's what this plot is showing, as you go down and to higher pressures, that electron Fermi energy is going to rise, and that'll drive electron captures. And so what you're seeing here is the proton number of the one species in your lattice dropping, whereas the mass of that material stays the same, until eventually you hit a point where you get to neutron drip. So the nuclei are too neutron rich to hold any more neutrons. They start to shed neutrons into a gas. This is the boundary where you've entered the inner crust. And then as you continue to compress, you can eventually drive fusion, picnonuclear fusion in the crust, until you basically washed out anything that could be called nuclei, and you enter the core. Okay, so let's go back to that crust and let's talk about the outer crust in particular. So I mentioned, stars freeze. So why doesn't our sun freeze? The short answer is that it's too hot and it's not dense enough. But if you take any material and if you make it cold and you compact it, it's going to crystallize. So in the case of neutron stars, the factor that we're interested in is this gamma. This is basically a ratio of the Coulomb repulsion between nuclei and the thermal energy. And so right around this value of 175, there was kind of a decade of work to study this. You have this sort of first order phase transition where nuclei will either crystallize, forming a sort of lattice, or there'll be this nice sort of fluid and liquid thing. So these are your pairwise distribution functions. That's just GFR. Okay, so again, and it's sort of related. This is the one component plasma, right? You have some ion charge. It's got some sort of lattice spacing. This is proportional to your density, and you have a temperature. And if you put all these numbers together, you get this ratio of Coulomb to thermal, and that'll tell you whether or not you are going to crystallize, essentially. But that's just sort of the one component model. Things get much more tricky very quickly when you look at these systems, these accreting X-ray binaries. So you have some hot companion star, and you've got mass flow onto a neutron star, which is being heated. So there's accretion onto the surface of the neutron star, and that's going to heat the crust, and it's going to produce nuclear reactions. So we had a great talk earlier this semester from Zach on this, but just as matter accretes, it's compressed, and it's buried, and it's heated, and you get this episode of explosive nuclear burning, and you basically produce this heavy RP ash. So down here you can see that we've got some sort of CNO to start it, and then you break out, and all these reactions up your table of nuclides to sort of produce this mixture of heavy material. But that's not the end of the story. There's this hydrogen that's flowing from the companion onto the neutron star, and it winds up in the ocean. And so it accumulates there, and it eventually burns, but it's buried by material arriving later. And so as that material is buried, it's eventually going to sink down, and it's the pressure on it's going to increase, and the density is going to increase until it wants to crystallize. And you're going to produce this solid crust beneath the ocean. And so the conventional wisdom is that the crust is going to be enriched in sort of the heaviest material that the RP ash burns, the high Z, the high charge material, whereas the lightest material is going to somehow preferentially remain in the ocean. Okay, so there's a long chain of events that relates sort of, and I want to put this up for everybody in JINA. There's the astrophysics of the accretion. There's nuclear burning that's in reaction rates that determine the exact nuclear burning in the RP process, which in turn sets the crust composition, which in turn, that the crust structure is going to set thermal conductivity. So there's a huge interplay between nuclear physics and astrophysics, and also material science and condensed matter in a sense. Studying the crust is sort of a condensed matter problem, which is where we get this astromaterial science from. Okay, so we hear about this in every other JINA seminar, but I'll review it very quickly. The RP ash has a large impurity parameter. That's just sort of the variance in the charge of the material that forms as a result of the RP process. The ash is impure. It's a big mixture of isotopes, while observations would tell us that the crust more likely has a low impurity parameter, something closer to 10 or less. So how do we reconcile this, that the nuclear burning is telling us one thing, but observation should be telling us another thing? And I think the canonical wisdom is to phase separate it, is to say that you have this block of solid and this block of liquid. You can do these very cool calculations with the free energy and the tangent curves where you find coexistence, and you find that material will separate out, and canonically that was that the heavy high Z material will settle into the solid, whereas the light low Z material will be preferentially retained in the liquid. So to give you, again, this sort of illustration, accretion comes into the ocean and it burns, and that makes your orange RP ash, and you can phase separate that. So if we remember our primary colors, yellow and red add up to make orange, so we're just going to take the orange and we're going to split it into the red and yellow. The yellow is the high Z material, and the red is the low Z material. So we want to say that this yellow material ends up somehow deposited into the crust, but that makes a problem because we're just sort of pretending that this low Z material that's retained in the ocean sort of goes away. But if it accumulates in the ocean, how does that make sense? You have to put it somewhere. So there's a lot of ideas. Maybe it creates convection in the ocean to keep the composition of the ocean one way. Another alternative is that it's deposited in layers. Sure, it phase separates, but as it's buried, the pressure increases until this low Z enriched liquid also forms solid chunks. And you would end up with these sort of layers, or these grains, each preferentially, or each, how do I say this? Each of which is purified individually next to each other. So there is a net effect of a low impurity parameter in the crust. You can speculate for days and days, but I think there's a big question that's unanswered at this point in time, which is just, is the composition of the crust time dependent? There's a million different hypotheses, and I don't think we're totally there yet, but it's an important question because it's going to govern a lot of what we want for interpreting observations. Okay, so I mentioned a paper a minute ago, which was McKinven et al. 2016. And in that paper, they calculated the phase separation that you should expect from the base of the ocean after the RP process. So they take a bunch of different compositions following a burst of RP burning, and they say this is how it should phase separate. So in this plot, what they're showing you here is the ratio of sort of the abundance of an ion in the solid as opposed to the liquid. And what they see is that for this accretion rate of 30 Eddingtons, you have this enrichment of the high Z material in the crust with the low Z material staying in the liquid. That's essentially what this plot is showing. And that agrees with the conventional wisdom. But they found a weird case in their analysis. They found for this one specific low accretion rate that it's actually sort of inverted, is the light material is what's enriched in the solid and everything else seems to have stayed in the liquid, which they worried might have been an artifact of their model and how they calculated it. So Andrew and Ryan, they sent us an email. They said, hey, can you simulate this? Can you simulate the phase separation and see if this is an artifact of our model or if it's a real thing? So we have these predictions, and we can just use molecular dynamics to simulate that phase separation. You know, we just say, hey, there's some Coulomb force between any two ions, and you just do molecular dynamics. And so for those who aren't too familiar with molecular dynamics, the basic idea is for computer simulation, you just take some point particles, you can calculate forces between them. So these black lines are the forces, and eventually you get the net force. And then you use that to integrate acceleration and velocity, and you move the particle. So you're moving particles. And so you do this millions and millions of times with lots and lots of computer hours until you get some sort of respectable composition that you can do some science with. So to study phase separation with molecular dynamics, what you want to do is you want to start with two blocks of the material that have the same composition as the RP ash. And you're going to take one and you're going to crystallize it so that it's the material falls on a lattice, and you're going to take another and it's just going to be a liquid. And then you're going to sort of staple these two simulations together, and you're going to try to run as close to the melting temperature as possible so that you can have this coexistence. And you're going to let the ions diffuse freely between the liquid and the solid, and then eventually you're going to see that some sort of unique composition emerges in each the solid and the liquid. So in this image right here, I'm showing you that canonical example where the solid has high Z material and the liquid has low Z material. Okay, so this is an example of one of those simulations. Each one of those little dots that you see, that is an ion. I just want to thank Don Barry from our group, who's the one who did the simulation. But you can see there's this very clear lattice structure here, and there's this very clear liquid here.
Matt, we have a question. Matt?
Yes.
I have a question about you're doing these phase transitions in the crust with the molecular dynamics, but the heat capacities of a classical system differ from that of a quantal system. Do you have a feeling for what difference that makes in your predictions?
Not particularly. For the classical system, we can only sort of have the heat capacity of the ions. We can't explicitly include the heat capacity of, say, electrons, for example. So no, I actually can't comment on that. I don't have a good sense of it. Did that answer your question?
Yeah.
Okay, great. So we have these classical simulations. There's a solid and there's a liquid, and you just let them evolve. And you'll also notice that we had some phase separation that occurred inward in this crystal. There's these little blocks in the middle. It has a sort of jelly-filled center where some of the phase separation actually didn't want to get out, but it formed a little bubble inside, which kind of skews our results a little bit, but not too badly. So we can track just by dividing this simulation into two. We can say, here's a block that's the solid, and then here's these other blocks that's the liquid. By dividing it in two, we can just count the numbers of each ion in each of those respective regions, and we can see if they're becoming enriched as a function of time. So that's what this is. This is a function, or this is the simulation time on the x-axis, and the y-axis is that same ratio of abundance in the solid to the abundance in the liquid. And what you find is that for this specific case of m dot being about 0.1 Eddington, you are enriched in the solid with Z of 10, 11, and 12, whereas you're depleted in everything else, exactly like McKinven 2016 predicted. Admittedly, the enhancement isn't that strong. Ours is about a 20% enhancement for the strongest one, which is Z of 12, whereas McKinven predicts closer to 50%. And we can probably attribute that to that cream-filled center in our crystal, which throws us off a little bit. But qualitatively, we're reproducing the same sort of physics. And again, you know, sort of this is that same plot for our MD simulation and putting it side by side with McKinven 2016, and it's qualitatively, you know, very striking, at least. And so I'd like to believe that MD simulations can reproduce the phase separation in this weird case, and we can confirm that it's not an artifact of the model, but this is a real thing. So what this means for the canonical wisdom, where we say that it's the high Z material that's settled into the solid and it's the low Z material that stays in the liquid, you want to rephrase that a little bit, and you want to say instead it could be the most abundant material from the ash that settles into the solid, and the things that closest to it in charge also settle with it, whereas those that are too different in charge are pushed out and would make up the liquid. That's one way that you could potentially interpret this. So there's also plenty of other compositions that do agree with that canonical wisdom that the crust is enriched in the high Z material. You know, all these other bits of burning give you that same enrichment that you should expect. And that's cool, so we can simulate those as well without doing the full phase separation. You know, we can just make a crystal of that material to study its properties. So here's an example of one of those crystals. Each one of these points over here is an ion, and so these stripy lines that you see, those are sort of Bragg planes. So this is a simulation of about 100,000 ions. And if you zoom in, you get a view that looks like this. This is sort of a projected flat, so you can see along some of the lattice planes. And the different colors are denoting different charges, essentially. And remember that this isn't, you know, a perfect crystal. This isn't one species. There's a lot of gunk mixed into it that doesn't have the right charge for this lattice. And you see a lot of these blue particles. Hopefully this shows up well on your screens as well as it's showing up on mine. These blue particles can be interstitial. So these are the very low Z material that has made it into the crust. So there's a lot of interstitial material. And I just want to emphasize, you know, you can have lots of different things going on in a crystal when you, you know, do molecular dynamics. There can be, you know, grain boundaries. There can be, you know, impurities. There can be dislocations in a lattice. There's a lot of things going on, and we're trying to capture some of that physics with these molecular dynamic simulations of the crystal. Okay, so one important property of these crystals is we can get the diffusion coefficients. If you just simulate an equilibrium crystal, eventually someone is going to hop a lattice site. They're going to basically bump into their neighbor and they're going to move to their lattice site, and that allows for diffusion in the solid. And so I've calculated these diffusion rates for what is this, a few different compositions, and we find a sort of broken power law behavior. There's the light material, you know, Z less than about 10 or so that's up here, that's, you know, maybe 2 orders of magnitude faster than the bulk of the material in the solid, which is much slower, or closer to 10 to the minus 5 or 10 to the minus 6 in units of the ion sphere radius times the plasma frequency. And it's this, you know, very general sort of pattern of this broken power law. All the simulations, compositions I've checked tend to show this. And Andrew Cumming comments in this McKinven et al. 2016 paper that this diffusion rate of 10 to the minus 6 can give you about 3 centimeters of diffusion while you're still at the top of the crust if you wait about 100 years. So if your layers, remember how I mentioned that sort of layers could form if the liquid also crystallizes later. If these layers are about 3 centimeters thick, they could get washed out just by diffusion in the crystal. And potentially, you know, with an order of magnitude variation in diffusion coefficients, there's a lot more to explore on this problem. Yeah, and I guess this is just re-summarizing that last slide again, but the low Z material is diffusive, that's these things, and they're also interstitial, that's the blue points in this plot, whereas the higher Z material is sort of non-diffusive, you know, 3 orders of magnitude slower, and they tend to be found on lattice sites. Radial distribution functions are another way to study the crystals in these simulations. These are the pairwise correlations between particles and their nearest neighbor. So each one of these peaks, this is a nearest neighbor, this is a second nearest neighbor, and this is a third nearest neighbor. And I'm doing it, I'm comparing between species. So this is the charge of the 2 species, so for their nearest neighbors. And one thing you notice is that this first peak is shifted ever so slightly for different charges. So the magnitude of these peaks is due to the relative abundances. I haven't properly normalized this plot, and I apologize for that. But I think you can still see the effect that I'm talking about, which is that when you look at a pair of high Z charges, for example, the green line, which is Z of 12 and 18, the peak is shifted further out. Whereas you look at closer or smaller charges, and the peak is shifted to a smaller radius. And so the way you interpret that is that the Coulomb force is weaker, so the interparticle separation would be less or greater depending on their the product of their charges. But notably, the second peak is not shifted. So this tells us that there might be some sort of screening going on so that the second and third peaks aren't shifted. So this is just a sort of nearest neighbor effect. So if you wanted to draw a cartoon, you could say, let's imagine something with some average charge, and that would be this top row here. And if you throw a impurity onto a lattice site, a high Z impurity, you would want some elbow room, and the greater Coulomb force is going to push away this nearest neighbor, who's going to in turn push his second nearest neighbor just a little bit. And I'm arguing that I don't see that in my simulations. Instead, what I'm seeing is that if the second neighbor is unshifted, perhaps there are short-range correlations between these impurities, so that if you have a high Z impurity on a lattice site, maybe his nearest neighbors are slightly smaller Z, so that your second nearest neighbor is unshifted. So that's one way I could potentially interpret this plot of G of R. The last thing, I guess, to talk about for hard astromaterials is the static structure factor. The static structure factor is the thing that lets you go from crystal structure to crystal properties. Ultimately, it's a bunch of math. You take an integral after getting the static structure factor, and you can plug it in as the Coulomb logarithm to get the thermal conductivity. And this is really important for reasons that everybody knows that I'll talk about in a minute. So I want to calculate these things directly. This isn't something that I have to report on right now. It's something that's a work in progress. But I'd like to be able to give you what I expect the thermal conductivities to be in the near future, and to be able to compare to what the models predict and the models use. And maybe we'll see that there's a systematic effect where we might need to use a slightly higher or lower effective thermal conductivity based on what the molecular dynamics says. Again, this is a work in progress, so hopefully I'll have these numbers ready in time for the JINA meeting, the Frontiers meeting in February. So to revisit the low mass X-ray binaries, so yeah, they can accrete and you can have bursting, but if the accretion stops for whatever reason, the crust will start to cool off. And it's this cooling that's been observed and reported on for quite a while now. And it tells us something about the composition of the crust. So this is MXB 1659. This is Brown and Cumming 2009 is where I stole this plot from. And you see that the crust, these black points are the observation, the crust was cooling and then it sort of flattened out. And so what you might argue is that the crust was conductive, it cooled very quickly and found equilibrium with the core. So that's what this sort of horizontal line right here would be. This would be re-equilibrating with the core. And so this tends to agree that, yeah, there should be a low impurity crust. And I'm going to revisit this plot, this exact same plot, in a matter of just a few minutes. So I think that's everything I had to say about the hard astromaterials and the crystals and the phase separation. And I'm going to move now into the deeper part of the crust, which is the inner crust and the nuclear pasta that's found there. So to again review, the crust is this crystal, but the core is this ball of uniform matter, like a giant nucleus. So there's got to be some sort of nuclear phase transition in between where you go from having isolated nuclei to bulk nuclear matter. And those phase transitions are now sort of identified to be these pasta phases, where you take nuclei and you compress them into the inner crust until eventually, the spacing between nuclei is comparable to the nuclear radius, and they're going to fuse and they're going to rearrange to form these long cylinders, which we call sort of spaghetti, which can contain many thousands of nucleons. They have the cross section of about one nucleus, but they're incredibly long. And if you compress those, they can in turn snap together and fuse, and you can make plates that look sort of like lasagna. And if you keep going, eventually you get these sort of phases that are uniform matter with these voids in them. So the entire concept of this just comes from frustration. The idea is that there is a competition between the proton-proton Coulomb repulsion, which is in the nuclear matter, and there's a strong nuclear attraction between protons and neutrons. So the nucleons adopt these non-spherical geometries near the saturation density just to minimize their surface energy. And again, this is that picture from the Hashimoto paper from 1984 predicting spheres, cylinders, slabs, cylindrical voids, and spherical voids, which we now call sort of the pasta phases. And again, I love showing this plot because it is a remarkable agreement between theory and more theory. We've got, the same spheres, cylinders, slabs, cylindrical holes, and spherical holes that you would have predicted in a paper 30 years ago. Okay, so I have an animation that I like to show just to help you orient yourself. I again do molecular dynamics of nuclear pasta. To give you a sense of a length scale, here's like a gold nucleus, so it's fairly small. And this is a block of uniform nuclear matter very close to the saturation density. And what's going to happen is the simulation volume is going to expand, and so it's going to decompress, and you're going to observe these phase transitions as a function of density. So as I start to play, what you're going to see is there's going to be these holes that are opening up. So you actually see this sort of Swiss cheese looking thing. All of these circles that you see, those are holes. And the holes are going to fuse as the density drops lower to make these tunnels. So that's sort of like an anti-spaghetti phase. And those holes eventually fuse to form these blanks between these parallel plates. And so this is, this lasagna, these slabs, which are very long-lived. They occupy a pretty large part of the phase space. So the density gets low enough that they in turn fission, and you get these cylinders, these spaghetti noodles. And if you pay close attention, this is a nice hexagonal packing right here. There's a very nice lattice structure to these. And as you get down to, about a tenth of the saturation density, these things are in turn going to fall apart, and they're going to make what are approximately, individual nuclei. And so that's going to happen right about now. And there we go, and we have a nice lattice of nuclei. And it's important to notice that the separation between these nuclei is very close to the nuclear radius. These are very, very densely packed nuclei. Okay, so I have done surveys of the parameter space just in temperature, density, and proton fraction. We can produce a lot of different materials beyond just these regular things. So this is a shorthand I've adopted. This is not sort of technical or in the literature by any means, but I just use R to denote regular because they're sort of symmetric, the spheres, cylinders, slabs, and so forth. And then I've also got things that are topologically or geometrically similar, but can have some topological differences that I call irregular. So irregular lasagnas, these large plates, they're sort of buckled at angles. And if you go in some other directions, if you turn down the proton fraction a little bit, you can also get holes to open up. You make waffles. There's also these things which we call defects, where there's sort of these filaments that are connecting the lasagna plates, which I'm going to talk about more in a minute. So unlike in the outer crust, where it is useful to use the just Coulomb's law with a screening factor, we have to define some nuclear potentials. That's what these are. These are these sort of pseudo-Yukawa looking things. If you're familiar with a Leonard-Jones potential, these things are qualitatively very similar to a Leonard-Jones potential. There's a strong attraction between neutrons and protons, a weak neutron-neutron interaction, and then the protons also repel with this additional Coulomb force. The parameters here are just chosen to reproduce the binding energy of select nuclei. And again, it's just a short-range nuclear force with a long-range Coulomb force. And maybe, your alarms are going off in your head and you're saying, hey, wait a minute, Matt, that doesn't make any sense. You can't use, classical molecular dynamics and point particles to study protons and neutrons in a neutron star. And I would say you're probably right. That is a very fair criticism. And if you don't like the idea of using classical molecular dynamics, I can also let you know that people do these fully quantum simulations with Hartree-Fock. And in a way, the classical simulations can help them. We can do these small simulations with a few hundred particles, and they can sort of wrap a Gaussian around them. So this was made with a classical MD code, and then they can you can fold a Gaussian over it, and then you can evolve this as your initial configuration in Hartree-Fock, and you'll find that it's relatively stable. So the classical simulations and the quantum simulations have fairly good agreement, and the classical simulations can also enable the quantum simulations by really accelerating them, by giving them good initial conditions to start from. But to give you a comparison between the classical and the quantum MD, the quantum simulations are limited by computational power. You can't have too many nucleons because then it gets too computationally expensive. So comparable simulations would be 800 nucleons in a quantum simulation and 50,000 in a classical simulation. So just being able to do these big simulations is a huge advantage that the classical mechanics or the classical simulations have over the quantum. And we can also go big. 50,000 is normal for us. We have done simulations with hundreds of thousands, even up to 3 million particles. We hope to describe these soon and have an article out on them. But we're very proud of the fact that this is the largest simulation of its type ever done of nuclear pasta. And nuclear pasta is important to many processes. I know I haven't emphasized this much yet, but for thermodynamics, just like we said, the impurity of the outer crust determines how it cools. So too does the conductivity of nuclear pasta determine how it will cool. Additionally, magnetic field decay, if electrons are scattering from the pasta, can cause the magnetic field to decay. That was described by Pons in 2013. I think the title of that paper was Too Much Pasta for Pulsars to Spin Down, which I really liked. If pasta is elastic and is very sticky, you might be able to make little mountains, buried mountains in a neutron star. And because it's very dense, if they're big enough, you can have a persistent source of gravitational waves from mountains on neutron stars. This next point, we just put a paper up on the archive yesterday, so I didn't have time to fully assimilate it into my slides, so I'm not going to talk too much more about it. But it can affect supernova neutrino transport in a very dramatic way. So there's the archive link there if anyone's interested. And also, you know, the time scale for the R process is order milliseconds, which is much slower than the time scale for pasta to form. So if you eject you know, matter near the pasta density during a neutron star merger, in principle, you do have chunks of pasta, and material goes through pasta phases before it eventually forms the seeds for the R process. And so again, I want to revisit this idea of defects, like I discussed for the hard astromaterials. In a soft astromaterial, you won't have these, you know, grain boundaries perhaps, or interstitials or impurities, but you can have things that aren't regular or symmetric. So for example, that would be like these filaments that connect you know, these plates. And the reason that's important is because electrons don't scatter from order, they scatter from disorder. You know, if you have a perfectly ordered crystal, you have this nice block wave and everything is normal and happy. It's only when you throw in something, only when you throw a wrench into the engine does scattering start to happen. So these defects will essentially act as a site for scattering in neutron star inner crusts. And I also want to take a moment and just throw a completely unrelated tangent out there. This same structure, these defects, was recently observed in living beings. So I show these slides side by side, these pictures. This is my simulation of nuclear pasta, and this is actually an electron micrograph of the endoplasmic reticulum from inside of a mouse. So one is observation and one is theory, and they have this very striking resemblance where you have these helicoidal ramps connecting the plates. And so this paper finally got accepted, and it's published in PRC. It just went up last month. And I tell you, the pop science writers went crazy with this one. If you tell them that the inside of neutron stars looks like the inside of living creatures, which in turn looks like a parking garage, they can write about that. And so there's a lot of really fun pop sci articles that were written about this. But it's a cool paper for scientific reasons because it shows that there's some sort of universality of self-assemblies. There's some sort of process that makes these two things, even though they have very different interactions at work, want to produce this same sort of helicoidal ramp in parallel plates. Back to your regularly scheduled physics talk, the defects in pasta can act as a site for scattering, right? So you can imagine doing simulations of perfect pasta and pasta with these sort of spiral ramps that connect them. And you can imagine that, you know, electrons are sort of flowing, right? You have electric currents. So electrons would be more inclined to scatter from a defective piece of pasta. And again, this is something that Pons talked about in his 2013 paper, which is that if there's an electrically resistive layer, you can make the magnetic field decay before young neutron stars spin down too much. So they all have these spin periods of, what, 12 seconds or something, I think. So we can do this sort of calculation of the electrical conductivity of the crust in the same way that we do the thermal conductivity for the ions. You calculate a static structure factor, and then you do an integral to get the Coulomb logarithm, and then you just sort of plug that into these three things. And again, this is all very boring and kind of mathy, so I'll just sort of jump to the punchline. We've done this. So there was this paper that we, wow, Schneider 2016, that was earlier this year, that's so recent. That we show that for example, thermal conductivity can drop by, what is this, about, you know, 30% or so with defects and so forth. And we also find that this is comparable to having an impurity parameter of order 30 in the inner crust. And so that's going to be relevant for crust cooling. So I want to take a moment and just sort of do a toy model to put this side by side to help give people some context that haven't seen this a million times yet. Imagine that you have two houses and they're heating up in the sun. Don't even worry about neutron stars right now. Just worry about this toy model. And there's a cold reservoir in the inside. It's kept at a constant temperature with an air conditioner, and there's a huge heat capacity. The only difference between these two houses is that the red house has a layer of insulation underneath that first wall. So eventually nighttime is going to come around and the sun is going to go down, and that outer wall is going to cool off. So the heat can go two directions. It can go out, it can be radiated away, and it can also sink inwards. And so the house with the layer of insulation, less heat is going to sink inwards than in the blue house. So what this means for the temperature of that outer wall is that the blue house will cool much faster and come into equilibrium with that cold reservoir, the air conditioner, than the red house. The red house will take a significantly longer time to cool because it has this insulating layer. Okay, what does this have to do with the neutron stars? Again, imagine these low mass X-ray binaries when the accretion cuts off. You can wonder if there is an insulating layer underneath the outer crust. And you can see this in the late time cooling of these X-ray binaries. So this is from a paper, Horowitz 2014, where we basically say, where we revisit MXB 1659. So this is the same data that I showed you earlier, but with one extra data point out here. So the blue curve is that curve I showed you essentially before. There's a low impurity parameter for the outer crust, and then there's some constant temperature for the core. And so, within 1,000 days or so, it eventually flattens out and it's re-equilibrated with the core. But if you put in an impure pasta layer, if you say that the very bottom of the crust is this highly impure layer, you can fit this last data point that was observed at about, what is that, the 3,000 to 4,000 day mark. And so it's still cooling 3,000 days out. And so this is really striking. I think that this is observational evidence for the presence of pasta. Admittedly, it's fitting one data point, but it's very cool nonetheless, and it seems to agree with what we've predicted from theory. Okay, so in the end, to interpret observations of neutron stars, we have to develop these microscopic models, and the way we do that is with these molecular dynamics. And so we simulate these things, and we calculate the properties of the star, and we're hoping that's going to allow us to interpret observations in the future. So thank you very much for your attention. Do you have any questions?
Yeah, thank you very much for the great talk. If you have questions, please indicate so in the chat.
We would have a question, Ingo.
Okay, yeah, please go ahead then.
I thought that's easier when nobody is chatting. So, Hendrik.
Yeah, I have a question. You mentioned that there's pasta ejected in neutron star mergers, and I was curious if you foresee any impact on the later nucleosynthesis. Does at the time of nucleosynthesis, is there something that remembers what happened during the pasta, or?
That's a really good question that I've asked myself, and I don't know if that's actually been too thoroughly explored yet. The paper that I wrote on pasta nucleosynthesis was basically taking our pasta model, and like in that animation I showed you where I blew up the pasta, you end up with these nuclei, and so I said, okay, maybe those can be our process seeds. And I just said that it matches nuclear statistical equilibrium. So that was the extent of the work that's been done on that. But I think you do make a really interesting point that there may or may not be an effect that's stamped into the R process on it. So one question you could ask is, does the neutrino flux through the pasta, if the pasta has a high neutrino opacity, does that change your proton fraction as you're being ejected by being sort of in this critical regime of interacting, of weak interactions, essentially. So the short answer is that I don't know, and that I think it's interesting. Did that answer your question?
Yeah.
We have another one here. Bill has a question.
Yes, I was curious about you have a pasta phase, right? And it may depend on how deep in the neutron star, on what kind of pasta phase you're talking about, spaghetti or lasagna. But what is the transition temperature that you would expect to evolve from a pasta phase to something less colder?
Could you say that again? The temperature where you expect the pasta phase to do what?
The pasta phase, most calculations, the pasta phase is essentially at 0 temperature. But then if you raise the temperature, say if you were at a temperature of 1 MeV, you expect to see pasta phase is still at 1 MeV. If so, at 1 MeV, how about 2 MeV? When does this start when does the thermal fluctuation just wipe out this order?
Right, and that's a very good question. I can tell you in my classical pasta model, it freezes and it forms a glass at 0.5 MeV, and that it also melts and becomes this sort of disorganized gas at 2 MeV. So that's a consequence of the classical model, and that's sort of that's an artifact of the classical model. That's not the real physics. But people have gone and they've produced phase diagrams at finite temperature, and Farouk, 10, right? 10 MeV is approximately the washout point where it just becomes disorganized protons and neutrons. There's a few good papers. I think Bastian Shatrumpf, one of his papers, does a pasta phase diagram, and there might be one more that I can't recall off the top of my head. But 10 MeV, I think, is a good upper limit for where pasta is going to fall apart. And that's also with Hartree-Fock. That's not with classical models. So that's why I trust the 10 MeV figure over what my model gives.
Yeah, but you would imagine that, I mean, that 10 MeV number is almost a temperature where you just don't have clusters in the inner crust. But this long-range order that you have in terms of the pasta, doesn't that actually begin to just fluctuate away at temperatures below 10 MeV?
Yeah, and in fact, that's a really good question, which is why let me scroll back. Which is why we think that these simulations are important to do the really big simulations and look for finite size effects. If there is basically, I want to imagine there can be grain boundaries, and so if there's some thermal limit where you can get around being a perfect piece of pasta, potentially at higher temperature or at finite temperature, you can imagine there would be sort of grain boundaries in pasta. I don't know if that answers your question too thoroughly, but that is, yeah, you are on sort of the right track.
Okay.
Oh, and Chuck is trying to say something.
Some sort of liquid crystalline light order, and it probably stays ordered at these temperatures for accreting neutron stars, because the system is so dense. The Coulomb parameters tend to be pretty high just because it's high density. So if you have clusters, the solid-like order may persist at an MeV or relatively high temperatures. It's not 10 MeV, but it's certainly temperatures for these accreting neutron stars.
Did you hear that all right? That was Chuck, who's across the room. Hopefully that came through okay.
It came through just fine.
Any other questions? You can just go ahead if you have one. If not, let's thank Matt again for the great talk.